Hey guys, sorry for the big delay between video 1 and video 2. I started having some issues with the video not wanting to upload, and I got really mad and just had to walk away from it for a while. But we're trying again, okay? So hopefully this one will actually work. But yeah, we're gonna pick up and talk more about spontaneity. So how do you know? So we talked about sort of the difference between spontaneous and non-spontaneous, but how do you know if something's gonna be spontaneous or not? Well, I mean, first right off the bat is the number one thing that matters, and we've already talked about this previously in this class, but is energy. Are you lowering the energy of the system? So one of the first things you may want to look at is delta H, right? Enthalpy. Is enthalpy negative? Because if enthalpy is negative, then that means that energy is being released, which means it's an exothermic process, and all exothermic processes are spontaneous. All exothermic processes are spontaneous. All right? But endothermic processes, which are processes in which the energy of the system goes up, these have positive delta H's, and most of these aren't, but some of them are. So how? Well, first thing right off the bat, it can't be like super endothermic. It can't be like a really high positive delta H, but it could be a little bit of a positive delta H, right? And how we can handle this slightly positive delta H is the fact that you are increasing the entropy, right? And we had talked about this before in this class again, but you've increased the entropy, which means you've increased the randomness or the disorder of the system, and that can make up for some of the delta H. Not all of it, but it can make up for some of it. So what that means is we need to study entropy more. Before we just said, all right, cool, we've learned a little bit about entropy, and I told you we'd come back to it. Well, now we are back to it, and we need to understand entropy. Okay? So first of all, entropy, the symbol for entropy is a capital S. Entropy is a thermodynamic function, just like energy and enthalpy are. We're going to introduce another thermodynamic function in this class, G. And the importance of G is it relates enthalpy and entropy to one another, H and S, because those are super duper important, but it's important that we could study them at the same time, and G allows us to do that. Okay, but we'll get to G later on. Right now, we spent all of, or a large portion of the first chapter on thermo talking about H, enthalpy. Now we need to talk about S, entropy, a lot more as well, right? So what entropy is this is defined by Australian physicist, or Austrian, sorry, not Australian, Austrian physicist Ludwig Boltzmann. And capital S entropy is equal to his constant, which I'm sorry, yes, I understand little k is rate constant, but it's also the Boltzmann constant. And where that number comes from, the 1.38 times 10 to the negative 23rd joule per Kelvin, is the gas constant, 8.314 joule per mole Kelvin, divided by Avogadro's number, 6.022 times 10 to the 23rd. That's where the number comes from. So what does that mean? It's talking about gases and the energy per mole and the fact that it is temperature dependent, and it takes into account how many molecules are in a mole. So right off the bat, you notice that entropy is a little different than enthalpy. Enthalpy was an energy per mole, or just an energy, right? But this is an energy per Kelvin, which means that this is temperature dependent. Okay, this function is temperature dependent, and this Boltzmann constant is going to be multiplied by the natural log of W. And what W is the number of energetically equivalent ways to arrange the components of a system. Basically, how many things can you come up with that are all exactly the same, right? If I say I want 10 M&Ms out of a bag of, I don't know, 30 M&Ms, there's a lot of options there as to which 10 you could hand me, right? Or one way we like to talk about entropy is playing poker, right? So I don't know if you've played poker before, but it's a card game. You know, you're trying to win or at least trick someone into thinking you have a better hand than them and getting them to jump out of the game. But basically, the hand that wins in poker, the highest point value hand, is something called a royal flush. And what a royal flush is it's all the face cards and one suit. Well, there are 4 suits in a deck of cards. There's hearts, spades, diamonds, and clubs. Okay, so there's only 4 chances for you to get a royal flush. So there's not a lot of entropy associated with a royal flush. But if you consider just like a card of like a hand of nothing, so you have cards that do not even make a pair, there are like a million combinations that can give you nothing. So that's why they talk about having a poker face, because 90% of the time you're playing poker, you ain't got nothing, right? So there's much more chance W is going up as far as having nothing, which means there's a lot more entropy associated with having nothing than having actually a good hand, right? So let's keep talking about this. So let's consider having a mole of an ideal gas at a particular temperature, volume, and pressure. So we have to remember that gases are constantly in motion and that they expand to fill their container via the kinetic molecular theory. And we're going to say that this one particular set of conditions is the macro state of the system, right? But how many ways can we make this macro state? All right. So imagine that you've taken a picture with a camera, right? So in the old school days, that's all we had just like, the throwaway cameras, or the cameras that you went and they developed the whole thing and just gave you pictures back. You didn't even get the little cheap crappy camera back. Yeah. So just a singular picture, whereas now, I mean, if you've got an iPhone, you've got live mode and all sorts of crazy stuff, or you got a camera that's super high speed. It can take like 100 pictures in the time frame another camera may only take 1, right? So the sum of all those pictures equals the 1, right? So the high-speed camera has a lot more entropy associated with it, or the live mode has a lot more entropy associated with it than the regular camera, because it's got more options, right? So microstate is W. As W goes up, so does S. And we're just talking about like pictures, right? I mean, I don't care highest, speed camera you've got, you're still only going to be taking like maybe 100 or so in a second. But imagine that we're talking about Avogadro's number of molecules, 10 to the 23rd. This is numbers that we can't even like fathom in our brain how big of a number this is. And you could have multiple moles of something. This large of a number is very, very hard to actually like simulate. We have computers now that allow us to simulate numbers this large, but we can only do it via classical physics and classical mechanics, which is solving Isaac Newton's equation. We can't do it using real physics, which is quantum mechanics yet. It's too complex. The math is too complex, even for the computing power that we have. And you may think we have very powerful computing power. But this idea that entropy increases with the number of microstates, this idea is so important still to this day, and was so important that Boltzmann figured this out that it's actually engraved on his tombstone. Okay, so like these people who laid the foundation for what we understand is the field of science, they were honored in their time, and they're still honored to this day, because who knows where we would be without their discoveries. So what's an example of what I'm talking about dispersal, right? Well, if you look at System A has 2 particles, both in a 2 joule energy level. Okay, that's the only option for them to live. 2 plus 2 is 4. But in System B, we have a 3 joule energy level and a 1 joule energy level. And 1 particle's in the 3 joule and 1 particle's in the 1 joule. So 3 plus 1 is 4. But take a look at System, so they both have 4 joules, but System B just says 1 particle is in each, which means you could move the particles around. And if you can move the particles around, then that means that there's a second microstate, which means System B has a more dispersal of the energy. So System B has a greater amount of randomness or a greater amount of entropy. Okay? So the simplest definition of entropy is that it's an increase in randomness. A more appropriate definition of entropy is that it's an increase in the dispersal of the energy, which basically means more microstates, right? So what is this going to sum up as? Well, last chapter on thermo, and we've already reviewed it, we learned that the first law of thermodynamics states that energy is conserved. So the energy of the universe now is exactly the same as the energy of the universe when it was created. Here's Dr. Stover's shorthand for the second law of thermo. Entropy ain't. Entropy is not conserved, guys. For any spontaneous process, which we live in a spontaneous world, the entropy of the universe is increasing, which means that we are living at a much more random place than what the world started with. This idea, the second law of thermo, I'm not telling you to believe in it. I'm not even telling you if I believe in it, but I'm telling you that this is one of the bases of the idea of the Big Bang Theory, how we started from sort of this one concept, because there's always been this increase in entropy of the universe, and that's what the second law of thermodynamics states. Okay? So entropy, like enthalpy, it's a state function. We can represent it as a delta. So delta S equals the entropy of the final minus the entropy of the initial. Now, just like with enthalpy, figuring out S is kind of difficult, so we got to have some other ways to figure it out. But we'll talk about that more as this chapter proceeds. But let's do one more sort of talk through of what we mean by this idea that entropy is increasing in the second law of thermo. Well, take a look at these three macro states, A, B, and C, that you see on the slide. Now, to be honest, A and B could only be initial conditions, right? Because if that valve was open between those two cylinders, those gas particles would immediately equally distribute, right? So A and B are like initial conditions. C would essentially be like a final condition. But take a look at state C. If there's 4 particles generating state C, how many options can you make that give you state C? So think of numbering the particles. How many arrangements of those 4 numbers could you come up with? And the answer is 6. Okay, there's 6 different arrangements of those 4 numbers. All right? Because you could have 1 and 2 on the left, 1 and 3, 1 and 4, right? Or you could have 2 and 3, 2 and 4, 3 and 4 on the left. And then obviously the same sorts of things on the right. So what does that mean? That means that macrostate C has 6 microstates that define it. There's 6 different arrangements that give you that macrostate C. Whereas if you look at state A and B, the sort of initial conditions, there's only 1 microstate that can define them. That's why gases spontaneously expand. By spontaneously expanding and filling the room, they are increasing their randomness, they're increasing the number of microstates that define them, which means they're dispersing their energy more. Which means they're overall lowering their energy, but in a different way. Right? All right. So that's it for this video. So we're going to end on this slide, and we'll pick up in the next video moving forward. All right, so Stover out. See you in video 3.